Have you ever wondered how computer programs run? They're like instructions written in a language computers understand. But what if you want to run a program written in a different language? That's where virtual machines come in. Think of a virtual machine, or VM, like a translator for computers. Virtual machines are like software versions of real computers. They have their own virtual CPUs, memory and storage. This allows them to create a controlled environment for running programs. Just like there are different types of computers, there are different types of virtual machines. Let's explore two main categories. First up, we have system-based virtual machines, or SVMs. These are like complete computer systems within your computer. They allow you to run entire operating systems, like running Windows inside your macOS. On the other hand, we have application-based virtual machines, or AVMs. These are designed to run specific programs or applications. SVMs provide a high level of isolation and security, while AVMs offer portability and ease of deployment. It's like choosing between a guest house for long-term visitors or a workshop for your weekend projects. Each serves a different purpose.
Java, being a popular programming language, uses a special kind of application-based virtual machine called the Java Virtual Machine, or JVM. The JVM is a crucial part of the Java ecosystem, providing a runtime environment that allows Java applications to run on any device or operating system. The JVM is a key component of what makes Java so portable. It abstracts the underlying hardware and operating system, allowing Java programs to run anywhere without modification. To understand how Java works, let's break down its three main components: JDK, JRE, and JVM. Each of these components plays a vital role in the development and execution of Java applications. Think of JDK as a toolbox for Java developers. It provides all the necessary tools and utilities to create Java applications from scratch. JDK stands for Java Development Kit. It includes a compiler, a debugger, and other tools that help developers write and test their code. It includes everything you need to write, compile, and debug Java programs. Without the JDK, developers wouldn't be able to create new Java applications or modify existing ones. JRE, or Java Runtime Environment, is like the finished product you get from the JDK toolbox. It provides the libraries, Java Virtual Machine, JVM, and other components to run applications written in Java. It's what you need to actually run Java programs on your computer. The JRE ensures that Java applications have the necessary environment to execute properly. The JRE includes the JVM and a bunch of pre-built libraries and files that Java programs need to work. These libraries provide essential functionalities that Java applications rely on. Now, the star of the show, JVM, is like the engine that powers Java programs. It is responsible for converting the bytecode into machine code that the computer's processor can execute. It takes the compiled Java code, called bytecode, and translates it into instructions your computer can understand. This translation process is what allows Java to be platform independent. Together, the JDK, JRE, and JVM form the backbone of Java's architecture, enabling developers to create powerful and portable applications. This trio ensures that Java remains a versatile and widely used programming language across various platforms and devices.
One of the coolest things about the JVM is that it's platform independent. This unique feature sets it apart from many other programming environments. This means that a Java program can run on any computer that has a JVM installed, regardless of its operating system. Whether it's Windows, Mac OS, Linux, or any other OS, the JVM ensures compatibility. But how does the JVM achieve this magic? It's a fascinating process that involves several steps. Well, when you compile a Java program, it doesn't get turned into code that your computer's processor can directly understand. Instead, it undergoes a transformation. Instead, it gets turned into something called bytecode. This bytecode is a universal language for the JVM. Think of bytecode as a kind of intermediate language that the JVM understands. It's like a bridge between your Java code and the machine's native language. The JVM acts like an interpreter, reading the bytecode instructions one by one and telling your computer what to do. This interpretation happens in real time, ensuring smooth execution. This is what makes Java so portable. You can compile your Java code once and then run it on any computer that has a JVM. This portability is a game changer for developers, allowing them to write code that can be used across various platforms without modification.
Section 5. ClassLoader, the Bytecode Weaver. Now let's talk about how the JVM actually loads and manages the bytecode of your Java programs. This is where the ClassLoader comes in. The ClassLoader is a crucial part of the JVM that's responsible for finding, loading, and linking Java classes. Think of the ClassLoader as a librarian. When you need a book, you go to the librarian and they fetch it for you from the shelves. Similarly, when the JVM needs to use a class, it asks the ClassLoader to find and load it. The ClassLoader has three main tasks: loading, linking, and initializing. The ClassLoader plays a vital role in the JVM's ability to dynamically load and manage classes, making Java a flexible and powerful language.
Section 6. Memory Management in JVM. Memory management is like keeping your room tidy. Just as you need to organize your belongings to find things easily, a computer needs to manage its memory to run programs efficiently. When you run a program, it needs space in the computer's memory to store its data and instructions. This space must be managed carefully to ensure that the program runs smoothly without running out of memory. The JVM, or Java Virtual Machine, is in charge of managing this memory space efficiently. It ensures that memory is allocated and deallocated as needed, preventing memory leaks and optimizing performance. Think of the JVM's memory as a big container divided into several compartments. Each compartment has a specific role in the overall memory management process. Each compartment has a specific purpose. Understanding these compartments helps in grasping how the JVM handles memory. First, we have the method area. This area is crucial for storing the core components of your program. This is where the JVM stores the bytecode of your classes, as well as information about methods and variables. Bytecode is the intermediate representation of your Java code that the JVM executes. Next, we have the heap. The heap is essential for dynamic memory allocation. This is the largest part of the JVM's memory, and it's where objects are created and stored. Whenever you create a new object in your program, it is allocated space in the heap. Then, we have the stack. The stack is vital for managing method execution. Each thread in your program gets its own stack, which is used to store method calls and local variables. This ensures that each thread can execute independently without interfering with others. When a method is called, it's added to the top of the stack, and when it finishes executing, it's removed from the stack. This last in first out LIFO structure helps in managing method calls efficiently. Finally, we have PC registers. These registers are crucial for instruction execution. Each thread also gets its own PC register, which keeps track of the next instruction to be executed. This helps in maintaining the flow of execution within each thread. The JVM does all this memory management automatically, so you don't have to worry about it when you're writing Java code. This automation allows developers to focus on writing efficient code without getting bogged down by memory management details.
Section 7. Execution Engine, the Heart of JVM. The execution engine is the heart of the JVM. It's responsible for actually executing the bytecode of your Java programs. It's like the engine in a car that makes it go. The execution engine has three main components: the interpreter, the JIT compiler, and the garbage collector. The interpreter is like a translator that reads and executes bytecode instructions one by one. It's relatively slow, but it's very flexible and can start executing code immediately. The JIT compiler, on the other hand, is like a turbocharger for the JVM. It analyzes the bytecode as it's being executed and identifies frequently executed code blocks. These three components work together to execute your Java code efficiently and effectively.
Section 8. Garbage collection, keeping Java tidy. As we've seen, the JVM's heap is where objects live. But what happens when an object is no longer needed? That's where the garbage collector comes in. The garbage collector is like a janitor for the JVM's memory. It's responsible for finding and removing objects that are no longer being used by the program. The garbage collector uses a clever technique called mark and sweep to find unused objects. It starts by marking all objects that are still reachable from the program's roots, like local variables and static fields. Garbage collection helps to prevent memory leaks and ensures that the JVM's memory is used efficiently.
Section 9 JVM, the cornerstone of Java's success. The JVM has played a pivotal role in the widespread adoption and success of Java as a programming language. Its platform independence, automatic memory management, and robust security features have made Java a popular choice for developing a wide range of applications. The JVM's ability to run Java code on any platform has made it possible to write once and run anywhere. Furthermore, the JVM's automatic memory management has greatly simplified Java development. Developers don't have to manually allocate and deallocate memory, which reduces the risk of memory leaks and makes Java programs more reliable. The JVM's combination of portability, ease of use, and security has made it a cornerstone of Java's success.
Section 10. Conclusion. In conclusion, the JVM is a remarkable piece of software engineering that has revolutionized the way we develop and run software. Its automatic memory management and robust security features have made Java a popular choice for developing a wide range of applications.